There we go.
Okay. Share my screen. Yeah, that's it, I guess. You see it?
Yeah, I can see it.
Yeah, okay. So today I'm going to talk about matching complexes of graphs. And I added manifolds because it was so broad. And my perspective is maybe from topological combinatorics or algebraic combinatorics, let's say. So I'm going to start with the main object. Let me see if my, does it work? Wait. Oh, it works. Great. So a simplicial complex is the basic object. So let's warm up with a short introduction. And I like to start with a picture as an example. So this facade is a simplicial complex. It's a building in Canada, and it really represents the simplicial complex of dimension 2 is. So we have triangles and maybe some edges, nicely glued. And so we can start with a formal definition. Well, simplicial complex is usually defined in abstract way, but here we want geometric definition because we're going to talk about manifolds, and they definitely come from geometry. So we have building blocks called simplices, and we define simplex with its dimension. So K simplex is convex hull of any K+1 affine independent points, and they are called vertices. So it's subject we are familiar with. When we have just one point, that's one simplex, zero simplex. When we have 2 points and convex hull, it's a line segment and one simplex, and so on. 2 simplex is a triangle, 3 simplex is tetrahedron, and so on. We have K simplex, and it lives in R to the K at least. And whenever we take a convex hull of a smaller subset, we say that it's a face of our simplex. And how do we build? Well, we say we just take a bunch of those and we glue them in a nice way. And to be formal, we say that simplicial complex K is a family of simplexes, so that whenever we put a simplex, let's take this tetrahedron in our complex, we put all its faces too. So that's the first condition. And the second condition says that whenever we have 2 simplices, let's say these 2 triangles, their intersection is nice. Their intersection is a proper face of both of them. So we cannot partially glue them. And that's geometry. What do we have from combinatorial perspective? Well, maybe I can go back and say that this statement, the complex is a family, reminds us that we can just look at these sets and their subsets. So abstract simplicial complex is any family that is closed under taking subsets. So we have some grounds at N, and we take some family of its subsets, and we say, okay, we need this property that whenever we have something in K and subset of it, then it is also in K. And how is abstract and geometric definition? How are they related? Well, one direction is very simple. When we have a geometric simplicial complex, we just take sets of vertices, and that's okay. But also another one is well known. Whenever we have abstract simplicial complex, just set of sets that satisfies these properties, we have geometric realization, which is a geometric simplicial complex. And good for us, each 2 geometric realizations, they are homeomorphic. So for somebody who looks at them, it's something like same, let's say. So further, we will not mention whether it is geometric or abstract because it doesn't matter for us. So these 2 correspond to each other. And what will we need later is definitely dimension. Dimension is something we would say it is dimension. So for a triangle, it is 2. And in abstract definition, we would say the dimension is number of vertices minus 1. And definitely dimension of complex is maximum of all dimensions of simplices. And there is another thing we are going to need, that's link. And that's what we're going to need a lot. So whenever we have a face, let's say just this dark blue vertex D, Link is set of all faces that form a simplex with D, but are disjoint from D. So here we have this light blue edge because we have this triangle with D, and we have this light blue vertex because we have this edge with D. So that's link, and I guess most of us are very familiar with it. And since we know what is simplicial complex, we're going to talk a little bit about general constructions of graph complexes. There are many of them. So general idea is that we have a graph and we assign to it a simplicial complex in many ways. But two most common is that we have a simplicial complex on a set of vertices V, or simplicial complex on the set of edges. And maybe one that we should mention at first is the neighborhood complex, because that is the complex that a lot of us used in the proof for that famous Kneser's conjecture that initiated topological combinatorics. He proved something like this, that connectedness, topological connectedness of this complex is in relation with chromatic number of a graph. And then he proved that completely combinatorial statement. And there are complexes that we are interested in, independence complex. We're going to talk a little bit about it, and the matching complex. And I just put these here, although we will not use them because they are quite well known. So how do we define a matching complex? We start from a matching of a graph. So whenever we have a graph, we can say that a set of edges is a matching if no two edges share a vertex. So just making pairs, this red set of edges. And now we can make a complex. So we have an arbitrary simple graph, and to define a complex, we need set of vertices, set of simplices. Let's look at this graph. So to each edge of this graph, we assign a vertex, right? And I arrange vertices not exactly as these edges are, because I wanted the complex to look nice. So the set of vertices of the complex is the set of edges of graph. And when do we put a simplex here? When we have a matching. So this is going to be our simplicial complex, our matching complex. And let's get used to it. So for example, I consider these three edges that form a matching, A bar, C bar, and E bar. And we have a simplex AEC. And that's what we do all the time. For example, we just have EB edge, because E bar and B bar, they form maximal matching, although it's not maximum among all matchings, but there is no other edge that is non-adjacent to both of them. And that's how we get to this matching complex. And here I'm going to mention another one, independence complex, because it's related to the matching. And I'm just going to use another name for the graph, let's say gamma, for some reason later. I look at this gamma, and at first I define what is an independent set. So, for example, set of these three vertices is independent because it does not contain any two adjacent vertices, right? And these independent sets, they are going to define the complex. So again, I have a definition, independence complex of a graph. Well, now vertex set is just vertex set of the graph. I, dearranged the vertices again for the same reason as before. And when do we put a simplex? Whenever we have an independent set of vertices. So A, Z, X gives us this one, and so on. Right. And why do we think about this? Because matching complexes are just one kind of independence complexes. How do we know that? Well, we take a graph G and we look at its line graph. So what is line graph? For each edge here, I have a vertex here, and then I connect two vertices if corresponding edges are adjacent. And that's how I get the graph. That's line graph. And now you see easily that when I have independent set of vertices A, C, Y, that correspond to a matching A bar, C bar, Y bar. And this is the relation. So matching complex of a graph is exactly independence complex of its line graph. So what we are investigating is just subclass of independence complexes. And just a little bit of history. I wrote some things, but I'm not going to bother you with all of them. So matching complexes, they actually appeared in algebraic group theory. Well, in some now and then they found some very various applications in representation theory, for example, to give some representation of symmetric group. And that's how people started to investigate their topology, because their topology, connectedness, it became important. But it's still very mysterious. For example, the first basic graph, complete graph, we know its topology just up to dimension 12. Later, we know that there are some weird torsions, but we don't know much. And there is another one, matching complex of complete biiterate graph. And it's also very well known. There are similar results for these two. But this one is also known as chessboard complex. For example, there is a result, just one of those results, that this complex is connected this much. And also there are many other results. Ziegler proved generality, that these complexes under some conditions are homotopy equivalent of edges of spheres, or so on. And these complexes are interesting because they have many, many applications in topological combinatorics. For example, that Verberg theorem that took a lot of attention, it was proved by some variations of these complexes and their joints and so on. And what else do we know about matching complexes? Well, we know them just for some very specific types of graphs. For example, Kozlov, he found homotopy type of matching complex for paths and cycles. Those are either contractible, either wedges of spheres. And there is general result that matching complex of a forest is a point or a wedge of spheres. And then with some colleagues, I investigated some specific kinds of trees. And beside trees, there are some results about grid graphs and polygonal light tilings and so on, but those are really specific types of graphs. So not so, let's say, not so explained object. But in all these cases, we started from a graph G and we investigated M of G. And now I'm going to think about reverse question. So which simplicial complexes can be seen as a matching complexes? So when you get a simplicial complex, can you say, oh, is this a matching complex or not? For example, the first one, you know, that building, the facade in front, is that a matching complex or not? And that's a very broad question.
Just a quick question, if I may.
Yeah.
So this, so you're taking the matching complex of a graph, and if you look at the one skeleton of this matching complex, so that's again a graph, right? So yes. Can you again form the matching complex of that graph, and if you take the iteration of that, does it give you different sort of graphs, or does it terminate?
I don't know answer to the question, but I think that a colleague of mine with the paper, he was interested in it, but I don't know if he answered that.
Okay, let's see. Okay.
I just don't know. I don't think it. I know that for some graphs it ends very quickly, like, okay. But I don't know like general answer. But thanks, it's a good question. And when we think about this question, we have some small motivation that comes from independence complexes. As I said, matching complexes are a subclass of independence complexes. And briefly said, we can say that everything is an independence complex. If not that complex, then its barycentric subdivision, it is an independence complex. So we just subdivide anything and it becomes an independence complex. So as a topologist, I could say that I can have every homotopy type among independence complexes. And whenever I have, for example, manifold or any object, I just subdivide it and I have it as an independence complex. But what about matching complexes? And there are some very basic observations. For example, that every matching complex is a flag complex. And this is like proof.
Sorry to interrupt. Can you go back? I got stuck at this, at every barycentric subdivision can be seen as an independence complex.
Well,
is that trivial or?
Well, it's not really trivial, but if you
okay.
and try to look what you want to get, then you're going to see, and this is the construction, I can say. Well, you take your complex, you look at its poset, and that poset gives you a graph, right?
Mm-hmm.
You look at a poset and you connect two things if they are in the chain, right?
Mm-hmm.
And then you take complement of that graph. That graph
Right.
called
Right. Yep.
comparability graph, and you take its complement.
Yes.
And when you take its complement, action independent sets correspond to those chains, like vertex, edge, side, and that exactly corresponds to.
Yep, that makes sense. Okay, thanks.
You're welcome. So these are the basic observations. For example, this not triangle, but the boundary of the triangle, this cannot be a matching complex. Why? Because, well, this corresponds to an edge, 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 and each two of them are non-adjacent, so that means that they form a matching. And whenever we see something like this as a subcomplex, we know that that's not a matching complex. And there is another one we observed in the paper that we needed for later things. And that is that matching complex has no induced path of length 5. And I call those P6. I use subscript, use number of vertices as subscript all the time later. So the construction is quite simple. First, if we start with this path on 5 vertices, we can uniquely determine the graph that gives it as matching complex. And this is the graph. And if you want to add one more, this X, well, this should correspond to an edge here, which is non-adjacent to B bar, but adjacent to everything else. And that's not possible. So this is a small proof. And this is also a trivial condition to be a matching complex. Well, since this is a very broad question, we decided to look at a smaller class. And we said, okay, we're going to talk about manifolds. So which manifolds can be seen as matching complexes? And when I say manifold, well, we always talk about the space where you feel like you live in Euclidean space, right? So we just have to state manifold in terms of simplicial complexes, some kind of simplicial manifolds. And this is a definition. So what I'm going to use is that K-simplicial complex, and this is its geometric realization. And I say that something is simplicial manifold or triangulated manifold if its realization, and all of them are homeomorphic, right? It's homeomorphic to some topological manifold, something like this. So we know what we are talking about. So when we make it smooth, that's a manifold. This is the most common definition, but I need to mention two others because that's what we used. One stricter, one simpler. And those are combinatorial and homology manifolds. And they're not this short, but I just like to shorten it just to mention the main idea. Well, for combinatorial manifolds, we ask that whenever we are at a vertex or any face, we look at its link. At a manifold, you want link to have a link to be a sphere, right? And well, here you ask that sphere, that subcomplex is piecewise linearly homeomorphic to the boundary of a simplex. So very strict condition. And for a homology manifold, you don't need that much. You just need the link to have homology of sphere. And I guess that in higher dimensions, it's different. So we always know that combinatorial manifold is simplicial and it's homology. And for manifolds we live with, two-dimensional manifolds or three classes are same.
So, sorry, just because I'm not so familiar with PL homeomorphisms, is a cycle homeomorphic to a triangle? PL homeomorphic. Yeah. Okay, good, just to be sure.
So these things are okay.
Okay, thanks.
Okay, so we start with our questions. We have a homology manifold, and we ask if there exists a graph such that is matching complex. And let's start with looking at an example, a general example, any cross polytope. What is a cross polytope? Well, that's a boundary, the boundary of convex hull of set of, vertices of orthonormal frame and points opposite to them, right? And we want to think about this because this is a sphere, right? This boundary is a sphere. It can be in any dimension. And we have a nice description of this simplicial complex. We know that set of vertices forms a simplex when, if and only if, we don't have two opposite points in it. So we know how the graph should look like. We just need, for example, En to be adjacent to minus En when we look at the graph, right? And nothing else. And that's how we get that only graph that has this cross polytope as matching complex. Well, that's a graph that contains n copies of path on three vertices. And that's one of examples that are going to appear in the general theorem too. So it's a general thing, but we should start definitely with small dimensions, low dimensions. First, in dimension 0 as 0, just 2 points, that matching complex of two adjacent edges, right? And in dimension 1, well, if we look at manifolds in dimension 1, that's just circle, right? And as a simplicial manifold, it's just a cycle. And then this arrow, that's actually a small theorem. And it says that if cycle is a matching complex, then that's a cycle of length 4, 5, or 6. And corresponding graph is either 2 copies of P3, cycle C5, or K32. And I wouldn't emphasize these low-level examples if they are not important later. So we call these graphs basic sphere graphs. And here they are. And here are their matching complexes. Well, here maybe it's sphere because matching complexes are graphs again, but I guess it's right. And these graphs, they're going to be building blocks for all graphs that have manifolds as matching complexes. And that's maybe a surprising fact. So that's dimension 1. And later, we will need construction that is based on join. So I'm just going to remind you of the definition of join. So join of complexes at first, while it's a simple construction, we take 2 complexes, disjoint or disjoint copies, and we say we take all the unions of simplex from one side, simplex from another side. So all of them, a very simple thing. And why do we care about that? Well, because when we have 2 disjoint graphs, matching complex of disjoint union is exactly the join. So look at the figure, this is the proof, like graph G1 and G2, we have a matching here and corresponding simplex in its matching complex, a matching here, corresponding simplex. And then when we look at the disjoint union of graphs, well, then all 5 of them, they may make a matching, and that's exactly the join. And this is going to be a really useful small fact, but very useful. And what do we get from this fact? Well, let me remind you that here, from these small graphs, I get spheres. Well, very small spheres, but still spheres, S0, S1, S1. And what would I get if I took a bunch of copies of these small graphs? So I have join, and I know this fact, the join of spheres is again a sphere. And I mentioned other 2 facts because of later theorems. Join of a sphere and disk, it's a disk. And join of 2 disks, it's a disk again, and just with appropriate dimensions. So when I have many copies of graphs that give spheres and take disjoint union, I get a sphere again. And this is a small theorem that says that G is a disjoint union of basic sphere graphs, then M of G is a combinatorial sphere. And these are all manifolds, except of torus, that are matching complexes. So let's try to prove it. At first, this is the theorem for dimension 2. And in dimension 2, we said, well, if M of G is a 2-dimensional manifold, what graph G can be? Well, a combinatorial analysis show that it can be one of these three disjoint unions. So just cycle K32 and P3. And that's what we expected from the previous theorem, right? But we got one more. We got this K43, and M of G is a triangulation of torus. And that's why we were worried a little bit, because what happens in the larger dimensions then? Because, well, maybe then we're going to get some weird manifolds. But no, we won't. And to mention the idea that we are going to look at later, I'm just going to look closer at torus and this graph. So we have K34, and this is torus. You see identification of these two edges. You glue them and glue two vertical sides, and that's torus. And let's look at some vertex. This vertex 1. It corresponds to this edge, let's say. And now I look at its link, because link is a really important fact in the definition of manifold, right? Everything is defined in terms of links. So I look at this link and see, well, what does this link correspond to in the graph? And definitely these vertices, they correspond to edges that are not adjacent to edge 1 bar. And I see that that's it, nothing more, nothing less. And that gave us the idea for this lemma, link lemma, that is just a general statement of the previous fact. And it says, well, look at any simplex in matching complex and look at edges that correspond to those vertices. And then we see that link of that simplex, that simplex is another matching complex of a subgraph. Another very simple fact, but very useful later. So here in the picture, you see I choose this vertex. Well, I can choose any simplex, but I chose just a vertex. So this vertex Y, I look at its link. It consists of these two red edges. And these two red edges, they're just matching complex of this 4 cycle. That is exactly the set of edges non-adjacent to Y bar. So that's it. Well, the idea that we get here is that whenever we have a link, that is again a matching complex. And that's some idea for some kind of induction when we grow our manifolds, because in manifolds, we have sub-manifolds in them. And this is the general theorem. So what did we prove? Well, this is important, so I'm just going to state it briefly. Well, we have a simple graph G, and we know that M of G is the dimensional homology manifold. I emphasize here without boundary. And we proved that then G can be nothing more than this joint union of these basic sphere graphs. So just those small graphs and nothing more. And well, we started with a homology manifold, and we proved that we can get just these small graphs. So we actually proved that there are no homology manifolds which are not combinatorial among matching complexes, because this is a combinatorial D-sphere. And the proof is long, as all important proofs in this work. But I'm going to mention some main ideas, main ingredients. So let's start with our M. That is the matching complex of that G. What is our main goal? To prove that this G is disconnected. Well, we don't see it at the moment. Why is it our main goal? But we're going to see it at the end. So how do we prove that G is disconnected? Well, we have some kind of clever induction. At first, normal induction could not work here. Why? Because we could not start with dimension 2, because we have torus in that, and we don't want that. We want to base on cases when we have just basic sphere graphs and just spheres. So we're going to build our theorem, but with a clever induction. We will prove, along with proving our statement, we will prove the statement for spheres. And for spheres, it is true in dimension 2. So this is the statement we prove, that if we have a simple graph G prime, such that its matching complex is a D-1 sphere, then it is the disjoint union of those small graphs. And that is true in dimension 2 when b is equal to 3. And that's just a small clever spot. So that's what we know from assumption. And then we do something like this. We take a vertex in a manifold and we look at its link from two sides. From one side, we know from that link lemma, we got the idea that link of that vertex is matching complex of that subgraph. From another perspective, in the manifold, we know that link of that vertex is a sphere. Well, homology sphere, whatever, but that's a sphere. The sphere of lower dimension. And when we combine these things with our assumption, and we know that this, subgraph by assumption, hypothesis, is disjoint union of those small graphs. And this is the idea that I could extract for this purpose, because the proof is really exhausting at some points. To use that fact that in manifold you have a submanifold to prove something for a submanifold, and then you know that for a very large subgraph you have disjoint union of those small, and then you have something more, and there comes a combinatorial analysis, blah blah blah. Well, it is tough at some points, especially for manifolds with boundary. But let's say we do it, and we prove that this graph G is disconnected. And what now? Well, we know that the matching complex of G is joint of two matching complexes. And there comes a theorem from a long time ago, theorem from pure algebraic topology, that says, well, whenever you have a manifold, that is a joint of two manifolds. So now we are far from combinatorics. We just know a manifold that can be represented as a joint of two manifolds, and we know that these are simplicial complexes. The joint is constructed in that way. Then we know that this manifold is a sphere, and both of these small complexes are also spheres. And that's great, because we go back now and we say, aha, we have this homology manifold, joint of two manifolds, then these are spheres. And then by induction hypothesis, G1 and G2 can be presented as those disjoint unions. And then G can be presented in the same way too. And that's the proof. Well, I really try to extract the ideas and not to, write the entire proof. Please, if you have some questions, ask later. And here I can mention that there is another part of this theorem that is just the similar statement for manifolds with boundary. For manifolds with boundary, again, if we have manifold with boundary that is a joint, then that has to be a ball, and these two, K and H, they also have to be either spheres, either balls, but at least one of them has to be a ball. And that's something that is proved a long time ago. And what I like about this proof is that it combines these combinatorial aspects and these topological things. And this brings us to a second question, which manifolds with boundary are matching complexes of graphs. And the ideas is similar, just the proofs are more complicated and longer. So let's see the results. Well, again, I have a really nice small set of basic graphs. Just now I have much more of them. Well, I have this pet P2, matching complex is just a point. I have this graph, we already saw it. Its matching complex is P5. And I have this graph. It took some time to find it. We call it spider graph because you see some legs. Actually, we have paths P3 and veg at one point. And matching complex of this graph is a combinatorial disk. You can just play a little bit with it. It has a nice structure, one central disk and some disks glued along its sides. And these graphs, they generate, well, almost everything. And we use same ideas. We remember those facts that whenever we have a sphere and disk, join is disk. Join of two disks is again a disk. So we can take disjoint union of many of these graphs, and we are going to get disk as matching complex. But this sphere here reminds us that if we add some sphere graphs, those basic sphere graphs, they will not destroy anything. We can add them, and we are again going to have a matching complex, which is disk. Well, while we have at least one of these. So this is the theorem. If G is disjoint union of these graphs, any number of them, and any number of sphere graphs with at least one that gives disk, then M of G is combinatorial disk, combinatorial ball. And well, we would like to prove that combinatorial balls are everything we can get. But in dimension 2, some really weird things happened. We got 4 topological types: ball, annulus, Mobius strip, and torus. And I wouldn't read this definitely. I just stated it in case someone is interested in details, but there are several classes of graphs that give them. There are several, unusual graphs, and that's it. We have some kind of weird situation here. For example, I can show you a picture. You see this graph. It's not spectacular, and its matching complex is this one. But that's definitely the Mobius strip. You just glue it, and that's it. And at this point, someone would think, okay, here, if it's weird again, it's in dimension 2, what happens in higher dimensions? But in higher dimensions, everything is great again. So here is the theorem, and it says if we have a simple graph such that its matching complex is homology manifold with boundary now in dimension at least 3, then it has to be a combinatorial disk or ball. And again, the only options are those disjoint union of those small graphs, basic disk graphs and basic sphere graphs. And the proof is again specifies to skip that dimension 2 where weird things happen and just use the dimension 2 for spheres, because again links are spheres or somewhere disks. Yeah, and then I stated some questions that arise naturally. Well, the first question is, okay, we looked at matching complexes, and matching complexes are just some subclass of independence complexes. What could we say about independence complexes? That's a natural question, although I don't find it so interesting, because we already know that we can subdivide independence complex, any complex and get independence complex. But it's kind of natural one. But there are more general questions that I found somewhere summarized. Found that it stated that these can be tough, hard. For example, what are the homotopy types of all matching complexes? So can you get everything with a matching complex? Or independence complexes give more homotopy types? Well, that's a strong question. Maybe we can say something, less hard. For example, when do we have a torsion in a matching complex? Because those spaces we got are really nice. So when do we have, ugly things? Or at least, when do we have contractible complexes or spheres or something like that? Is planarity of a graph relevant? Is length of cycles? What is relevant for a matching complex? And I find it interesting that graph theoretic properties that are relevant for the structure of the complex. We should answer something because I asked that at some point. Well, if this is a matching complex of a graph, and well, now it's an easy answer that it is not, because there is a induced P6 here. So, well, no, this building is not good. And well, these are some acknowledgements, and well, thank you.
All right, thank you very much for that talk. Are there any questions?
Maybe we can switch off the recording.
Yeah, sure. Why not? So I will switch off the recording now.